Graphical representation of motion. Let us try to represent motion by the following graphs. Let us interpret the kind of motion represented by these graphs. Look at this data. At 8 o'clock, an object covers a distance of 0 kilometer. That means the object is at rest and this is your reference point. You started taking observations at 8 o'clock in the morning. And after half an hour, you observe the object has covered a distance of 20 kilometer. Another half an hour, 40 kilometers. 9:30 it is 60 and 10 o'clock it is 80. So 0, 20, 40, 60, 80, 8, 8:30, 9, 9:30, 10. Equal time, equal distance. Let's plot the distance time graph for this kind of motion. Although we know equal distance and equal time means it should be a uniform motion. But how does it look on the graph? Let's try to find out. We plot the graph at 8:30 it's 20 and so on. These blue points show the points on the points of the table, right? So we observe that the graph for the uniform motion comes out to be a straight line which is inclined to time axis. Now if the graph is a straight line inclined to time axis, fine, so that means it's a graph of uniform motion. For a straight line we can always find the slope also. The slope of the straight line graph we can find by choosing 2 points A and B. Now let us look for the coordinates of the points A and B. Point A at X is 8:30, at Y it is 20. So point A, its coordinates are 8:30 and 20. And similarly for point B, the coordinates are 9:30 and 60. Fine. So now to find the slope, it's change in y-axis upon change in x-axis. That is y2 minus y1 upon x2 minus x1. Okay. And y2 was 60, y1 was 20. So 60 minus 20 and 9:30 minus 8:30. Fine. 60 minus 20 upon 9:30 minus 8:30. It's 40 kilometer per hour. That is slope of distance time graph gives us the speed of an object, because on y-axis we have distance, on x-axis we have time. Distance upon time, the units we are getting are of speed only. So we interpret that slope of distance time graph gives us the speed of an object. Fine. Equal distances are covered in equal time. So object is moving at a constant speed, and from the slope we found the speed of the object. Now this is a VT graph. Here also if you see, the time intervals are equal and the velocity intervals are also equal. So equal velocity in equal time. So let's plot the VT graph for this data. Right? So the VT graph looks like, again, a line inclined to time axis. It's a straight line inclined to time axis. And if we look for the slope of this straight line graph, we can again take 2 points A and B and note down their coordinates x1, y1, x2, y2. And similarly, we find the slope of the graph. y2 minus y1, x2 minus x1, fine. And y2 minus y1 means 20 minus 4, x2 minus x1 means 5 minus 1. So 16 by 4, it's 4 meter per second square. It's velocity upon time this time. Change in velocity with time, right? So meter per second square, that is slope of the VT graph, gives us the acceleration of the object. Fine. Slope of the VT graph gives us the acceleration. Fine. Okay. So now over here, let us calculate the distance covered by the object in the same graph. Fine. So I've taken the graph here again. Now we have to find the distance under this line. Okay, this graph, this line represents the data of the graph. So under this line, the area is like a right angle triangle. Fine. So this can be half of AB into BC, half of base into height, right? So it's velocity into time. Velocity into time means distance only. So that means this area should measure the displacement or distance in a, for us, in a straight line motion. In straight line motion, distance and displacement are one and the same. Now when we find the area under this line, we find half of what is AB. AB is 5, right? And what is BC? BC is 20 as per the graph. So half of 5 into 20, and we measure the distance as 50 meter. So we can calculate the distance covered by the object by checking for the area under the VT graph. Okay. Let us try to interpret the motion depicted by these graphs. Graph A is a distance time graph inclined to time axis. So definitely it's a case of uniform motion. And B and C, look at them, they are not straight line graphs. So they are curved graphs. So that means it's a case of non-uniform motion. In this fourth graph, the object is at same distance at any instance of time from the reference point. So it is not changing its position with respect to time. Hence, the object is at rest. In this particular graph, which is a VT graph now, in the beginning 0 to 2 seconds, you can say the object is at rest. The velocity is 0. It's not moving. Okay. Next 2 seconds, the object is uniformly accelerated. It is uniformly accelerated since it's a straight line graph inclined to time axis, and this 4 second to 6 second, it's a line parallel to time axis. That means the velocity is constant at this time. So if velocity is constant at this time, that means the object is in uniform motion. Okay. So this first part is at rest, then it is uniformly accelerated, then it is in uniform motion. It's moving at a constant speed. Look at this last graph for object A and B. This last graph helps you to compare the motion of the two objects. You can check which one of them is moving faster. Slope of A is more than slope of B. It's covering a greater distance in the same time as compared to the distance covered by B. So you can say A is faster than B. So this is how we use to compare the motion of the objects. So we conclude that slope of distance time graph measures speed, slope of VT graph measures acceleration, and the area under VT graph measures the displacement or the distance covered by the object in a straight line.